motion, there's always a frame of reference. And this is the question I always start off chapter 2, the kinematic stuff with. Is this desk moving? Depends on your frame of reference. Good. Yeah. If our frame of reference is the floor below it, nope. It's not moving at all. It's sitting right there. If our frame of reference is the sun, then yes, it most certainly is. It's hurtling through space at an astonishing rate of speed, as are you all. So whenever we talk about motion, we have to think in terms of frame of reference. So we can come up with an answer that gives us a relative motion. And the example that is most common is you're standing on the side of the road and a car whips past you at 60 miles an hour. Their relative speed to you is at 50 miles an hour. However, if you're in a car going the opposite direction at some rate of speed, then that changes the frame of reference. So when I was a kid, my dad was a ham radio operator. Many of you know what ham radio is? It's amateur radio. Yes, I grew up with a geeky electronics dad. And on family vacations, Dad always had a magnetic antenna stuck on the roof of the car. Okay, a little cable that went out through the back seat and up through the window, and a little magnet stuck on the roof of the car so that he could talk to people all over as we drove around. Great. And invariably, on some little two-lane road somewhere in the middle of Iowa, Illinois, you pick it, we'd be going down the road at 55 miles an hour. We'd meet a truck coming the other way, and the antenna, the magnet on the antenna, which had been holding up just fine at 55 miles an hour, would lose its grip. And the antenna would go hurtling down the back of the car, and I'd be responsible for snaking it back up, and then Dad would snap it back on the roof. Dad, why does the antenna blow off? So, you tell me, why does the antenna blow off? It only happened when we met a truck coming the other way. We're going 55 miles an hour for the last 600 miles. No problem.
That's the most
Okay, so it's not even necessarily so much about funneling, but you're on the right track.
I don't know how to
that's
explain
nothing to do with it, right? The trucker just knocked it over.
The trucker just stuck it. Yeah, I did that. No trucker pranks. No trucker pranks.
That's something I would do.
So why? I mean, it does have to do with it, but it really also has to do with relative speed, because suddenly your velocity and the velocity of the truck have an additive effect. And the air that you're each pushing suddenly seems to be moving a whole lot faster. It's really a relative motion thing. So, if you are going, okay, and you've all had this experience. You're out on Route 11. You're heading north at a law-abiding 65 miles per hour, because I know you all drive the speed limit.
Oh, it's
70 now.
Oh, God, that's so long. Okay. Well, you're all cautious and fuel-conservative individuals, so you're heading north at a nice, sedate 65 miles per hour. When I was a kid, it was 55.
Are you allowed to do that? That's like in King Trotter.
No, dear. No. 45. 45 is the lower limit. At 45, you have to have blinkers on, and below 45, you can be pulled over and given a ticket.
Nice try, Just kidding.
Just kidding. So, you're driving along at a nice, sedate 65 miles an hour, and somebody whips past you. Maybe it's Chris. Whips past you, and you know the phrase, "Pass me like I was standing still." And you've probably had that experience. You think, good Lord, how fast were they going? If I'm going the speed limit, and they just passed me like I was standing still, whoa! That's a relative motion problem. Now, their motion to you doesn't look all that fast from your frame of reference, but you know how fast you're going. So you know that they must be going significantly faster than you. Now, if you were standing still and you saw that car go by, it'd be a little blur. Okay? So those are the kind of problems we're doing now, and these are really just adding vectors. They only get complicated, of course, when we throw in what? Angles!
No.
Yay, angles!
I quit this.
No, you're not allowed to quit. Okay,
I've tried.
if you are going north at 50 meters per second, or 65 miles an hour, or 103 miles per hour, which none of you better ever drive, and the other car,
What?
don't want to know.
Yeah, I wanna hear.
You understand the consequences of force and sudden acceleration when, yeah, and yeah, anyway. We'll talk about that when the camera's off. If you're going 50 meters per second north and another car is going 50 meters per second north, what is it? And they're side by side. Does it look like they're moving at all? No. That's relative motion. It's really that easy. Okay? It is really that easy. And we have a little...
Yeah.
Why do you always think the worst?
Because you said it gets bad when you promote angles.
No, I just said it gets more interesting when you
You
involve.
said it
I
gets a
think
little
it's-
harder.
It's a little bit more
I'm
complicated.
guessing on other problems they both won't be going 50 meters per second.
No.
I'm just kidding.
Probably not. Probably not.
I got this 5 bonus points in the catapult going for me, I guess.
Oh, come on. Yeah, you got some bonus points from the catapult.
Do those go on that test? Like,
They just go in this 9 weeks. So,
So technically, in my mind, I can
in
put
your
them-
mind, you can put them there.
I'll just leave mine zero.
So that makes up for a test.
I can.
And you can do that too. It's up to you.
I can theoretically.
Thank you for bursting my bubble.
Wow. Okay, you know what? Apparently the video's not going to run. So, here's the big thing with relative velocities.
Oh, sorry.
The big thing with relative velocities is your subscripting. So when you're doing relative velocities, you want to make extensive use of those little subscripts. So, velocity of u to Earth. If you're in a car, if you're in a car traveling at 65 miles per hour, the velocity of u relative to the Earth is at 65 miles per hour. The velocity of the car with regard to the Earth, 65 miles per hour. The velocity of the car with regard to the u, zip. Okay? So you want to make extensive use of those sort of subscripts.
You're in the
If you're in the car,
I'm understanding.
Alright, my bad. I took it as
Oh.
same.
no, sorry.
Alright.
No, we could do one where you're standing on the side of the road,
Yeah.
and then it wouldn't be.
Then the car was 60.
Then the car would be 65 with frame of reference to you and the Earth.
Right.
What's neat is we can do these as pretty much straight additives. So the velocity of the car with frame of reference to you is going to equal the velocity of the car with reference to the Earth and the velocity of the car with reference to you. So we'll do some examples of these, and then we'll start some problems with angles. Oops. The unfortunate part about the frame of reference stuff, it's not like kinematics where you've got a set of equations. It's much more situational. So it's really drawing the picture becomes essential in order to understand what effect the vectors are going to have on one another. Making sure those of you who had problems initially with remembering to put arrows on your vectors, that'll lose you life and limb in this section. So make sure you're drawing good vectors, and that helps. That's it for chapter 3. So let's do some examples.